So my name is Sofia Finzi from Fondazione Icons. I'm a senior expert of the Horizon Results Booster, a free of charge service delivered by the European Commission, which the three projects that Sarah presented today, ZeroPM, PROMISCES and Scenarios, applied to, and that we went through together a path that I would like to briefly present to you today. But first of all, so we're going to give you a very short introduction of the Horizon Results Booster and its objective, the module that the three projects went through, and their path, and then we're going to see the agenda of the webinar, then giving space to the speakers. The Horizon Results Booster Service 1 modules A and B are aimed at pushing projects beyond their description of action. In fact, it's aimed at inspiring and exchanging solutions among sister projects to push sustainability of the project results. To that end, participants gain support from experts in order to additionally push their dissemination activities through clustering. So they are supported in reaching out to additional stakeholders to multiply their impact and outreach and engagement through the collaboration with sister projects. And that's what these projects have been doing. So together they bring results of their initiatives and they create a portfolio of results which are shared, both complementary and alternative. The practical objective of this module is to co-organize joint dissemination activities, both online and offline, to showcase these outcomes that the projects have in common and results. Finally, this service aims to help meeting the needs of the European Commission, so which is the clustering of projects which have commonalities. So to summarize, modules A and B of the Horizon Results Booster aim at boosting the outreach and the engagement towards the enablers of the project. Very shortly, in a nutshell, what is the Horizon Results Booster? It's directed to all types of EC-funded projects, so Horizon 2020, Horizon Europe, both ongoing but also completed projects. You still have time to apply and complete the services by October 2024. So there's still some months to be able to use this service. And you get this support and guidance from experts to produce tangible dissemination materials and activities. And you do it through these two complementary modules, which are Module A, so focusing in the identification of the project group in case it is not already formed, and the identification and creation of a portfolio of research and innovation results. And then once the group is formed, you work on a joint portfolio dissemination plan, which is then designed with the expert and then executed. This is together a joint path to, on one side, establish a collaboration if it is not already formed and consolidate it among the sister projects. And this, overall, we have an impact and sustainability of your key exploitable results. This is the final aim. So concretely, what is done with the Horizon Results Booster? You'll get support from experts, as I was saying before, in the creation of tangible outputs, where you then execute joint dissemination activities. So first of all, you co-design a joint dissemination plan, which you then execute together. You get to create a common visual identity and a written identity, and then this identity is applied to a set of graphic materials, which can be a joint logo, a joint video, and a fact sheet. You also get access to capacity building courses aimed at improving the dissemination skills of your consortium. And then you get support to deliver joint dissemination activities, which can be of different types, to the creation of joint events and webinars, such as it was the case for this cluster. You can write policy briefs, carry out social media campaigns, or you can get specific guidance regarding activities that you have already planned. So That's really a great support to contribute to carry out the joint dissemination activities, and also it gives you feedback regarding your dissemination outputs. Overall, this module lasts 120 calendar days, and hopefully the collaboration will last also after the collaboration, the service is concluded. The 3 projects that we have today, so ZeroPM, PROMISCES, and Scenarios, have been collaborating throughout Module B. So they have created a joint portfolio dissemination plan guiding their strategy as a cluster, and also a dedicated fact sheet and video were produced. Regarding the joint dissemination activity, which is in fact this webinar, the Horizon Results Booster has provided a set of materials that have been used for the promotion, especially of this webinar. For example, the agenda, some templates for PowerPoints, a social media campaign with social media cards, and in general, a strategy to design the webinar and the promotional activities. And finally, capacity building courses were delivered to improve the knowledge in terms of communication and dissemination. Before going through the agenda of today, I would like to show you one of the outputs of the module, which is the video that was produced within the service. And then we will give the floor to the speakers. I am afraid that the connection is not the best. So if you would like to see the video, we invite you also to go on the YouTube channel of the Horizon Results Booster. So going to the last slide of my presentation, I would like to introduce you to the agenda of today. So first of all, we will give the floor to Sarah Hale from the German Water Center to talk about the contribution of European research to evidence-based health policy. Then removal of PFAS from groundwater with high DOC concentration by Alexander Sperlich from Berliner Wasserbetriebe. Then Ali Batik with mobilization of PFAS from heterogeneous soils. An overview of transfer and conversion of PFAS during sedimentation by Ali Hidar. And then, sorry, there's connection issues. Then PFAS removal from water using combination of activated carbon by the German Water Center. PFAS in sewage sludge by Nasos Stasinakis. And finally, innovative treatment methods providing sustainable option for PFAS water treatment by Elena Hinrichsen. And finally, some space for questions. Thank you very much for your for hearing. I will now give the floor to Sarah for her first presentation.
Great, thank you, Sofia. Okay, if we just set up the slides. So I'm going to be quite brief. I just wanted to talk to you. Hopefully you can see my slides. There they are in presentation mode. I actually just wanted to give an overview of clustering. So Sofia touched on it briefly, and the 3 projects that you're going to hear from today are part of the Green Deal cluster. So what is the Green Deal cluster? It's basically these 3 projects plus 3 additional projects. And the 6 of us, we applied to 2 different research calls, and we were the ones that got funded. So there's over 75 partners and 52 million euros of funding. So they're actually quite big projects. ZeroPM lasts for 5 years and some of the other projects last for 3 years. But all of the projects, they focus on chemical pollution, specifically persistent and mobile substances and also chemical mixtures. So, I mean, everybody knows that chemicals are a part of our life. We need them and we want them in our products. But we also know, especially from recent research, that they're responsible for premature deaths. I mean, air pollution is one of the 5 main threats to biodiversity as well. So in response to some of these problems, the European Commission and the European Union has put forward the European Green Deal. So this is the policy package that's running at the moment, which aims to basically transition and reach climate neutrality by 2050. And the Green Deal also has a focus on chemical pollution. So they have what's called the Zero Pollution Action Plan. And this is one of the main things that we identify within this cluster. So we are looking at protecting the environment and human health, and we're also looking to encourage innovation. The picture that you see there on the slide, this is taken from ZeroPM, but it's heavily inspired by the Chemical Strategy for Sustainability, where we're really looking to move towards safe and sustainable chemicals as a first choice. So how do we work to contribute to society? The taxpayers have given us money to carry out this research, so that's a huge privilege. So obviously we're hoping that we can deliver tools and methods that support society going forwards. So we all work together looking at societal, environmental and economic issues, or the 3 pillars of sustainability. And what we're trying to do is we are working with providing improved hazard and risk assessment methods. We're looking at safer alternatives. We're focusing in on remediation methods, and that's what the webinar today is about. We're looking at innovative monitoring methods, and we're also providing decision support frameworks. So these are the things that we're all working towards in our different results. So I think I am going to, with that short introduction, just stop sharing my screen now, and we are handing over to PROMISCES. That will be the first project to talk. So we're having 3 presentations from PROMISCES, as Sofia said, and each of the presenters will introduce themselves as they present. So with that, I think it's Alexander's turn now.
So welcome everybody. Can you see my screen? I hope it works. My name is Alexander Sperlich. I am a senior research engineer from Berliner Wasserbetriebe, which is the utility providing water and wastewater services to the city of Berlin in Germany. We serve around 4 million people with water and wastewater. And I'm also the case study leader in PROMISCES. I'm leading the case study in Berlin here, and I would like to tell you more about PROMISCES and this case study in my presentation today. It's called Removal of PFAS from Groundwater with High DOC Concentrations. And I would also like to acknowledge the partners who are working with us on this case study in PROMISCES. This is the Competence Center of Water from Berlin, the Federal Environment Agency in Germany, the Federal Institute of Hydrology in Germany, and also Biodetection Systems in the Netherlands. And the PROMISCES is short for Preventing Recalcitrant Organic Mobile Industrial Chemicals for Circular Economy in the Soil Sediment Water Systems. It's one of the 3 sister projects which will be presented today. And it's coordinated by BRGM in France, by Julie Lyon. And you can see an overview of the partner institutions here. So it's a huge project with 27 partners all over Europe. And we have started the project in November 2021, and we will finish the project in spring next year. So we are quite on the last way of this project. And I'm happy to tell you more about it in the coming minutes. But on PROMISCES, I would like to tell you a little bit on the project objectives. The idea is, or the aim is, to identify how persistent mobile pollutants, for example PFAS, prevent the deployment of the circular economy in Europe, and which strategies help to overcome these key bottlenecks. We would like to integrate the PROMISCES results into a decision support framework, which considers resource recovery and water reuse and supports chemical management decisions. And the PROMISCES results should be translated into methods, tools, and guidance for efficient and feasible management of IPM substances. And we also would like to give recommendations for the implementation of relevant EU policy strategies and directives. And the work we are doing in this research project is along 4 circular economy routes and chemical emission pathways, which the different groups work on. And one is the semi-closed water cycles for drinking water supply at urban and catchment scale. This is the case study in Berlin I will be talking about later. But we're also working on wastewater reuse for irrigation and agriculture. We are also working on nutrient recovery from sewage sludge, on material recovery from dredged sediments. And finally, we're working on groundwater and land remediation for safe reuse in urban areas. So we're looking on these 5 circular economy routes in 7 different case studies in the project. These case studies are all over Europe, starting with Berlin, but we are also working in the case study 2 in the Upper Danube Basin from Vienna to Budapest. We're working in Italy and Bulgaria. We're working in Ancona in Italy. We're working in Orléans, France. And we're working in Catalonia, Spain, in 7 case studies. So this presentation will be about the case study 1 in Berlin, but after me there will be a presentation by Ali Batik on the case study 6 in Orléans, France, and then there will be the presentation by Ali Hidar on the results from the case study 5 in Ancona, Italy. So this is what the project is all about, and I would like to take you now into the case study 1 in Berlin, onto this in the semi-closed urban water cycle. What is this? What is the semi-closed urban water cycle? You can see here a map of Berlin. It's the capital of Berlin, and we have 900 square kilometers, and 25% of this is water protection area. And this is because we produce the drinking water in our in the area of the metropolitan area. And Berlin, as you can see on the map, is rich in water, but actually it's quite low in flow. The surface waters don't have much flow, and we have a low dilution of wastewater treatment plant effluents in the surface water, and that makes it hard to manage this water cycle. We have a semi-closed urban water cycle because we use the surface waters indirectly via bank filtration and artificial recharge for drinking water production. And we need to make sure that all barriers in the systems for chemicals are in place and working good to protect the drinking water quality. And this system is managed by us, the utility, but it's challenged by demographic change and also climate change, because we will see droughts and reductions of inflow to the surface water system, and the aging population will maybe increase their pharmaceutical consumption. So we have different stressors here giving us challenges for the sustainable water supply. And PFAS and PMT are one of the challenges here, and we are working on PROMISCES on these challenges. We are developing analytical methods to lower the limit of quantification for PFAS. With solid phase extraction, we would like to go down to below 1 nanograms per liter. We're also working on the detection of PFAS precursor substances in some parameters, for example, top assay and AOF. And we have in PROMISCES done a lot of monitoring on urban pathways, especially on industrial emissions into our sewer systems and urban runoff. So we are developing and testing passive sampling systems and use them in indirect industrial discharges and also in surface water. And we have made some sampling for urban runoff in the sewer system, as you can see here on the right-hand side. But this will not be the topic of today. Today, I will like to focus on the work we are doing on adsorptive removal of PFAS and other IPMT candidates in drinking water treatment. What we do here is we exchange with adsorbent manufacturers and look into the literature what might be the best technologies to remove PFAS. We do adsorbent screening by batch tests, we do rapid small-scale column testing, and we also do pilot and large-scale testing. And the idea is to give recommendations for the operation and design of groundwater treatment plants we are operating right now in the city of Berlin. And you can see this here. This is a groundwater treatment plant we're operating. It's treating a legacy HFFF contamination at a former airport site. And we're dealing with influent concentrations of different PFAS. You can see on the right-hand side, ranging between a few nanograms per liter up to 200 nanograms per liter for PFOS. The sum of the 20 PFAS is 417 nanograms per liter. And we have quite a high background DOC in this groundwater of 4.5 milligrams per liter. And you can see the treatment train which is employed in this groundwater treatment plant. Here we have a rapid sand filtration to remove iron and manganese. And it is followed by 2 trains of 4 stages of granular activated carbon adsorbers to remove PFAS. And one activated carbon adsorber has a empty bed contact time of 60 minutes, giving a total of 64 minutes for this treatment plant. And in PROMISCES, we wanted to investigate which alternatives are there and how we improve this technology to make sure that PFAS are retrained. But first, let me have a look at the performance of this treatment plant. You can see here the relative effluent concentrations versus the specific throughput in 1,000 bed volumes for different PFAS for these 2 treatment trains, for one treatment train here. And you can see that a quite early breakthrough, especially for the short chain PFAS, PFBA, followed by the longer chain PFAS as expected. But it's due to the competition with the natural organic matter, the DOC, we see a really quite early breakthrough below 10,000 bed volumes. Also, dissolved organic carbon breakthrough quite early at around 5,000 bed volumes. And the idea was now to screen for alternative adsorbents. So we especially studied a set of different activated carbons from different materials, but also surface modified clays based adsorbents based on bentonite and palygorskite, and also mixtures and zeolites. And we did also batch testing with ion exchange resins, different ion exchange resins. And the results you can see here on this slide. We tested for several industrial chemicals, including PFAS, but also pharmaceuticals and 2 sweeteners. And you can see here that the activated carbon shows the broadest efficiency. It can remove quite a lot of substances, but not to a very high degree, especially not for all the PFAS. And for the ion exchange resins, you can see that the charged PFAS are retained quite well, but we don't see that much removal for other industrial chemicals and also not for pharmaceuticals. And there are some mixed results for the alternative adsorbents for the surface modified clays. And based on this, we tested also the GSE, which is currently employed in the groundwater treatment plant. But we also choose then 8 of these adsorbents to go into a further testing using rapid small-scale column testing in the laboratory. We chose 3 activated carbons, 2 surface-modified clays, and 3 ion exchange resins, and went into rapid small-scale column testing. You can see now the results of this testing. You can see the specific throughput in bed volumes until the concentration in the effluent reaches 50% of the influent concentrations. So this is what we call BV 50%. And if it's below 5,000 bed volumes, it's shown here in red. And if it's above 100,000 bed volumes, it's shown in dark green, and you can see the difference then in between. And you can see here the same result, more or less. The activated carbons are not very effective for the removal of PFAS, but show show good capacities for pharmaceuticals and also other industrial chemicals. And the ion exchange resins and also the surface modified clays that we tested here are quite efficient in removing PFAS especially. And we selected 3 of these materials now for further testing at a pilot site. So we built a pilot scale installation right next to the large-scale groundwater treatment plant, and we're testing these materials further to see whether we can maybe combine them and where we can get the best removal of PFAS in the system. So what we see here is that the competitive adsorption of natural organic matter and PFAS leads to really low capacities at high DOC concentrations in the influent. We have tested several adsorbents based on surface modified clays and also ion exchange resins, and these show good results, and these can be a suitable alternative to the benchmark GAC applications. We have also seen that the potential for optimization by selecting different GAC products is probably low. The differences are not that great. Of course, we have chosen here GACs which are marketed for PFAS removal, but the differences are not that big. We have started pilot scale testing. You can see the picture here on the right-hand side of ion exchange resins and surface modified clays at the Berlin-Tegel site. This started this spring, and we will do target analytics of PFAS pharmaceuticals, also DOC and UV absorbents and anions. But additionally, our partners in the PROMISCES project will do a suspect screening and also toxicological tests. PFAS CARLOX will be done with samples from the system. And we would like to do a retrospective evaluation of the RSSCT scaling approach. And then we will get hopefully a comprehensive assessment under realistic conditions and can propose the optimal treatment train for the site, but also to transfer this to other sites, how to deal with groundwater with high DOC, which compete for adsorption capacity with the target substances like PFAS. So this is what I wanted to show you for the case study 1 in Berlin. And I would like to acknowledge my co-authors, Fiona Rickball, which is doing a PhD study here, and my colleague Regina Gniers. And with this, I would like to thank you for your attention. I'm happy to answer your questions later on. I would like to hand over to another PROMISCES case study, and I would like to give the word to Ali. Thank you very much.
Yes, good morning. Can you hear me, please?
Yes, we can
Yes.
hear you, Ali.
And can you see my screen?
Yep, all good.
Thank you. Okay. Just to be sure, can you see my screen another time, please?
Yes, we can.
Okay, thank you. So, good morning, everybody. I am Ali Batik. Today, I'm going to present you the mobilization of PFAS from heterogeneous soils, desorption by ethanol xanthan mixture. So let's begin. First of all, I'm going to present you the PFAS soil remediation technologies. So there are different technologies for PFAS soil remediation, which are presented in this graph according to the range of practicality and their stage of development. And as you can see with me, that soil flushing is representing a method, is the most promising method due to their high feasibility and the mature scale and cost effective. So what is the formulations that we proposed as a flushing solution in our study? Is a mixture of ethanol 50% volume fraction with the non-Newtonian fluid xanthan gum solution, the biopolymer. Our choice was based first on the previous studies that demonstrated that ethanol 50% could recover or regenerate activated granular activated carbon contaminated by PFAS. And second, thanks to the capacity of the biopolymer xanthan gum to change its viscosity, function of the permeability of the zone, which lead to homogeneous stable displacement, as it's shown in this experimental photos. So what are the aim of our study? First of all, is to show what is the effect of ethanol 50% volume fraction on the non-Newtonian behavior of xanthan gum solution. And second, to demonstrate what is the effect of xanthan gum solution on the ethanol 50% volume fraction in desorption rate. In order to characterize and select our fluid, a rheological experiment was carried out for the formulation proposed using a rotational rheometer. Then a batch experiment was made for a mixture of PFAS included PFOS, PFOA, PFBS, and PFAS at a concentration of 5 mg per liter, which represents the average concentration found in the groundwater, on a soil composed of 92% of sand, 5% of clay, and 3% of organic matter. Once the fluid was selected, we switched to one decanal experiment or desorption experiment, using the same condition as batch, which means the same mixture of PFAS at the same concentration and the same soil, and the characteristic of the soil are represented in this table, as it has a pore volume of 150 milliliter, porosity 39%, and 93 times 10 to power minus 12 meters square of permeability. So let's begin with the rheological behavior of the formulation proposed. So this graph represents the variation of the viscosity in Pascal second function of the differential rates for a different concentration of the polymer xanthan gum, which are 0.5, 1, and 2 grams per liter, with and without ethanol. And as you can see with me that xanthan gum exhibited a very strong non-Newtonian behavior, or what we call a shear thinning behavior, which means that the viscosity is decreasing when we're applying more shear rates. And also, the presence of ethanol for all the concentration of xanthan gum didn't affect the non-Newtonian behavior. So let's switch now to the other objective. This histogram represents the sorption percentage for each PFAS function of time. And as you can see with me that PFOS shows the highest sorption percentage, which is 56%, which is due to its higher water solubility, lower water solubility, 0.57 gram per liter, and its higher local W 5.26 comparison to all PFAS tested. And by comparing PFOA to PFAS, we can see that we have a slight difference in their sorption percentage, which was due to their comparable values of local W 4.59 for PFOA to 4.34 for PFAS. And finally, the sorption of PFBS showed the lowest one, 3%, which was due to its higher solubility in water, 46.2 gram per liter. This results was followed by the desorption results for the same PFAS mixture using different flushing solution, which are xanthan gum, the mixture of ethanol xanthan gum at concentration of 0.5, 1, and 2 gram per liter. In black, which are in red, in black the ethanol 50% volume fraction, and the blue is representing the desorption using pure water. And as you can see with me that ethanol in black could desorb more than 95% of different PFAS, and we had an additional of 3% of the removal percentage or recovery percentage for each PFAS by due to the presence of xanthan gum, regardless the concentration used. So view that we demonstrated that an improvement of desorption of PFAS in the presence of xanthan gum independent of the concentration used. Second, we had a conservation of non-Newtonian behavior of xanthan gum in the presence of ethanol. So the formulations that we propose to be tested in one decanal experiment is to use the mixture of ethanol xanthan gum at a concentration of xanthan gum 0.5 milligram per liter. Why? For two reasons. First of all, we have sufficient injection pressure in our porous medium from physical point of view, and second, taking into account economic aspect from industrial point of view. So let's begin first with the results obtained of one decanal experiment. I'm going to present first of all the case of PFOS. So this graph represents the breakthrough curve for PFAS obtained by after flushing of different solutions, which are in blue, the xanthan ethanol mixture selected, in red, the ethanol 50% volume fraction, and green is the pure water. And this histogram represents the total removal percentage for PFAS after using different flushing solution. The blue dashed line represents the transition zone between the injection of PFAS and the flushing solution. First of all, the sorptions that we obtained for PFAS in our 1D column, it was 89 plus minus 3%, which was very logic and due to its higher hydrophobicity and lower solubility in water. So let's begin. First of all, as you can see with me, that PFAS elution in ethanol with and without xanthan gum was faster than the one in water for 0.3 PV, indicating that PFAS solubility in ethanol 50% is higher than water. And by comparing the intensity obtained of PFAS in the solution of the mixture to the one of ethanol, as you can see blue to red, you can see that the PFAS peak in ethanol xanthan gum mixture is higher than the one of ethanol, which can be explained by the stable front displacement obtained after the presence of xanthan gum in the solution. And by comparing the results obtained as a removal percentage, you can see that PFAS was desorbed by 68% in pure water. This removal percentage enhanced and increased to reach 84% after adding ethanol 50% to the solution. And we had a desorption improvement by almost 10% due to the presence of xanthan gum in the solution to reach 93%. Well, the same results were more or less obtained for PFOA, as the PFOA elution in ethanol with and without xanthan gum was higher and faster than in water for 0.18 PV, indicating also that PFOA solubility in ethanol is higher than water. The intensity of peak corresponding to xanthan ethanol comparing to ethanol 1 is higher, also due to the stable front displacement. And talking about the total removal, we can see that PFOA was removed by 80% in pure water, increased to 93% after adding ethanol to the solution, and we have improvement by more than 5% due to the presence of xanthan gum in the solution. In case of PFAS excess, we had always also the same results as before, as the PFAS solution in ethanol with and without xanthan gum was faster by 0.25 PV than in water, also indicating that PFAS excess solubility in ethanol 50% is higher than water. And also, as you can see with me, that the intensity of the peak of PFAS excess in the polymer ethanol solution is higher by almost 15% than the one in ethanol, due also to the front displacement and the stable front homogeneous stable displacement obtained after adding xanthan gum to the solution. And by comparing the total removal of PFAS excess, we can see that the desorption of PFAS excess in water was 70%, enhanced by more than 10% to reach 85% due to the dilution of ethanol in the solution. And we have an improvement by more than 10% to reach 97% due to the presence of xanthan gum at 0.5 gram per liter in the solution. In the case of PFAS, which is the shortest compound tested in our study, and it has the highest solubility and the lowest absorption percentage in our study, which is 20%, the PFAS solution in ethanol with and without xanthan gum was more or less comparable to the one of water. As you can see, it's a little bit faster than water, indicating that the solubility of PFAS in ethanol is more or less comparable to the one of water. But by comparing the total removal, we can still see that PFAS desorption in water was 89%, increased to more than 5% to reach 95%, and still we have an affection of the presence of xanthan gum in the solution as the desorption rate increased to 98%. So in conclusion, we demonstrated that ethanol 50% didn't affect the non-Newtonian behavior of xanthan gum. Second, the batch experiment showed that PFAS sorption depends on the chain length and functional groups. Also, batch desorption showed that xanthan gum ethanol mixture enhanced PFAS desorption regardless of the concentration of xanthan gum. And the Connell experiment demonstrated that the enhancement in PFAS desorption after adding xanthan gum to ethanol. And I put it you here as a summary of the results obtained of one Connell experiment for the total removal. And as you can see that the formulation proposed demonstrated the most effective desorption rates obtained for HPFAS, as PFOA desorption increased from 80 to 99%. It was the same case as FBS from 89 to 98%. Also for PFAS success 70 to 97%, and the most important compound here, which is PFOS, from 68 to 93%. In terms of perspective, we are going to use the in situ remediation method by injections an innovative non-Newtonian fluid in this plurimetric pilot scale, which has a volume of 85 cubic meter. And as you can see in this photo, we have two injection wells, as we are going to inject our non-Newtonian fluid, and it will be spreaded in all the zone, and we'll have 3 recovery fluids. And the effluent obtained from this plurimetric pilot will be treated by different technologies, which can be the sonic cavitation, foam fractionation, and also maybe the degradation. Thank you for your attention.
Hey, hi everyone. I hope you can see my screen. My name is Ali, and I am from University of Polytechnic Delhi Marche. I'm a research fellow there, and I am part of the case study 5 and case study 4 in PROMISCES project. Today I'm going to talk a little bit about the remediation, about the case study 5, which is the overview on transfer and conversion of PFAS during sediment treatment. Okay, I'll start just by a small introduction. The project is within the concurrent project EcoCedra, which is a prototype sediment treatment plant. It's treating sludge from Ancona, and it is implemented to recover sediment as construction material to use for road embankments. Our goal is to understand the PFAS fate and distribution, to focus on the most contaminated fractions, and to see the removal or mobilization of PFAS substantially targeted fractions, and to enhance understanding of PFAS behavior in sediment transfer process. And then finally mitigate the PFAS contamination through removal or mobilization. Okay. The tested road sediments have been done in 2 sites. One of them is in Ancona, Italy, and the other one was in the Netherlands. As for the analysis that have been done, there was obviously the PFAS analysis, which had 30 target PFAS. Which had a level of quantification for 15 nanogram per liter for the liquid fractions and 15 nanogram per kilogram for solid fractions. Also, we've done some solids and liquids normal analysis, conventional analysis, and also the type of let's say sediment that we have based on which type of sand, silt, clay, and the percentage of total volatile solids. As for the in the lab scale, we did our work for EcoCedra as 3 types. One of them in the lab scale, and then with modified EcoCedra in lab scale, and then we had a pilot scale. In the lab scale, we had 3 types of washing: the normal EcoCedra treatment, which is started by the sediments, then moving to crushing and screening. Then there is 3 washing cycles, one of them with alkaline, one of them acid, alkaline, and then we have water. And then we have the drying, obviously, and then we have our recovered material and the wastewater that need to be treated. So in the EcoCedra treatment plant, as we said, we did in the base the first one, which is the normal one, which is the acid alkaline washing. Then we tried the hydrogen peroxide washing to check for the effectiveness and removal of PFAS, and then we make a modified EcoCedra, which is EcoCedra plus hydrogen peroxide washing. In the Ancona direct sediment at lab scale for the normal EcoCedra treatment, we noticed that after, let's say, you can see here, this is the raw sediments, and this is the removal efficiency. EcoCedra treatment had a good removal efficiency in terms of lab scale. And you can see the, let's say, the left PFAS concentration in the acid washing and the alkaline washing and in the fine washing also. We can see here clearly that there was also, you can see here this fluorescence test that has been done for the water of acid washing, alkaline, and the final washing, and you can see that it's more or less in line with the results of with the removal of PFAS that has been done in the acid and alkaline and the final washing. You can see clearly because fluorescence will show us the let's say the desorption of organic material, which happens exactly with the same concentration of the PFAS. Here we can see the same experiment that's been done for the Netherlands dredge sediments, also in federal scale. You can see that there is more concentration of PFAS, it's more contaminated sediments. And there was also, it showed similar efficiency in removal. But in Ancona, we saw that there was the more release of organic and PFAS in the acid washing. On the other hand, here in the Netherlands, it was in the alkaline washing, the more removal, and it's the same. You can see some of the concentration. The removal was not measured due to it was below the level quantification, but in any case, the removal was very good line. For the next one, which was the modified H2O2, as we said before, we tried the hydrogen peroxide washing to the sediment, and it has a good result. That's why we decided to modify Ecocedra treatment to check the effectiveness of removal. Ecocedra plus the hydrogen peroxide at lab scale, and we saw an increasing of the removal efficiency for the Ancona dredge sediments. You can see that the removal almost reached 100%. This is the one in parentheses, is the one calculated considering the analytical LOQ. In any case, it was a very high removal efficiency. We did the same experiment with the Netherlands sediments, also Ecocedra modified plus hydrogen peroxide. And you can see that we were able to detect more PFAS as the last time because due to the more contaminated sediments. Also, we had a very good removal efficiency, also increased very well, compared to the normal Ecocedra. Now I can show you the pilot scale of Ecocedra, which is already running. We have the sediments from Ancona port. It has crushing and screening, and then the coarse material disposal, obviously. And then we have remixing section. Then we have washing section with chemical dosing. We said we have 3 washing cycles as acid washing, alkaline, and the water washing. Then we have storage tank, filter press to remove as much water as possible. Then thermal drying of the sediments. Then we have the recovered material. The waste water will be collected, and then with the rejection also of the RO, because this is the water that is included, demineralized water into the system. And this water tank, wastewater tank, will be treated later for the destruction of PFAS. Sorry. This is one of the monitor campaign of the Ecocedra washing treatment at pilot scale. You can see that this is taken only from Ancona sediments, and you can see that also it was not as efficient as in the lab scale, obviously due to that scaling problems, but also it's pilot and running, which is increasing efficiency, let's say, over time due to the usage. But in any case, it was kind of a good removal efficiency for all the PFAS that have been detected. But as always, we had this problem to find a way to compare results very well, because as you can see, we have in each we have a different type of PFAS, which will make a different type of results, which is the comparison will be a little bit high. So by using the proposal of the EU PROM 2022, and to make a comparison in terms of PFOA equivalent, we were able to compare the Ancona Ecocedra, which is normal Ecocedra treatment, with the H2O2 hydrogen peroxide removal at different concentration, and also with Ancona plus H2O2. And as you can see from the results, there was kind of, removal reached almost 100 when using the modified Ecocedra or the hydrogen peroxide at 8 millimole per gram. And also, it was showing a good removal efficiency even at normal Ecocedra plant. You can see this is also as you can see, it's from the Ancona sediments. You can see in the pilot plant the removal efficiency, as we said, it was not as much as in the lab scale, but it had also very good results in removing. It was able, and this is all taken into account as PFOA equivalent, with knowing that the limit that has been designed was 77 nanogram per kilogram for PFOA equivalent based on the EU comp 540. We did the same comparison. Also, you can see it here in the Netherlands, let's say sediments. And but this one only in the lab scale without using the extravial plant, and using the same methods, we can see that the removal is a little bit less. This is due also to the high contamination that we have already. But in any case, there was, when we're using the etc. modified etc. plus H2O2 or the non-etc., we reached almost I mean 75% of removal, which is a very good comparison compared to the raw material that we have already. And in the final, we will have a very good material to be reused in concentration. I wanted to make it quick, and I don't want to spend much time, so I will go to conclusions. Our etc. treatment reached an overall PFAS removal of 87% for infant sediments and almost 53% for the Netherlands due to contamination. The PFAS removal is related to organic matter removal, so treating the sediments with hydrogen peroxide achieve better overall removal in non-chronic sediments, almost 100% with high concentration 4 and 8, and compared to the Netherlands, obviously due to the high contamination with 51 and 4.8 millimole per gram of H2O2. And the combination of ecosedral treatment and hydrogen peroxide washing demonstrated a very good results for uncloned sediments, reaching an overall removal efficiency of 100%. The Netherlands reached a lower efficiency, as we said, due to the high contamination. But this is a good result, as we have, because we know now that the PFAS in our case was related to the organic matter removal, which is shown exactly in the version that we showed before. By this, I conclude my presentation. Thank you for attention, and for any question, we can have it later at the stage in the webinar. For now, I give stage to ZeroPM, and thank you for listening.
We can't hear you, Marcel.
So now you should hear me.
Yep, lovely.
Now you should hear me.
Yep, now we hear you. Very good.
Okay, perfect. So hello together. Welcome to our webinar. My name is Marcel Riegel. I work at the German Water Center, and we are dealing with research projects and cooperation with water utilities, especially with drinking water treatment questions. And in my today's presentation, we stay at the PFAS universe, and I'm going to tell you about PFAS removal from water, and I'm going to present you a new treatment train we are testing, and this is the combination of activated carbon and ion exchange. So what is the background of our treatment idea? This is quite close to the work Alexander presented today. So if you would like to remove PFAS and other organic micropollutants during drinking water treatment, you normally use activated carbon filters. And the problem here is that some substances, some PFAS, they can't be removed quite well using activated carbon, and especially the short chain PFAS like PFBA and PFPEA, they can't be removed quite well, and they show a very early breakthrough if you would like to remove them by activated carbon. This is something Alexander showed today, and this is something you could see here on this right-hand side picture, where you see an early breakthrough of these two compounds. And therefore, we are trying to test new treatment approaches, and this is what my presentation is about. So the approach we tested is shown here. This is a treatment train where we started with an treatment with activated carbon. And after this treatment, we do a second treatment using ion exchanger. And this ion exchanger should not be used only one time and should be exchanged when it's exhausted, but it should be regenerated, that the adsorbed PFAS are desorbed from the exchanger, and then the ion exchanger could be used again. And therefore, we would like to decrease the material cost of the ion exchanger. And the idea is that the activated carbon as first treatment step could be used for a longer operation time and does not have to be changed when the first short chain PFAS break through this activated carbon. And with this treatment chain, we would like to reduce the treatment cost because activated carbon can be used for a longer time, and the ion exchanger could be used also for a longer time because we do regenerate them. Yes. So the first work we did was that we tested different ion exchanger materials and checked how good they could absorb different PFAS and how these PFAS could be desorbed again using standard regenerant regenerant chemicals. And out of these lab experiments, we selected some ion exchangers. We tested afterwards in a pilot plant. And altogether, we selected 3 different exchanger materials. Yes, and these 3 materials we tested in this pilot plant I'm going to talk about now. In total, we built up 3 different treatment trains or treatment streets in the pilot plant. One is that we used a single activated carbon filter as a reference. The second one is that we installed an ion exchanger, which we used only for a single use, so we did not regenerate it. And the third street was this combined treatment with first activated carbon filtration and afterwards an ion exchanger, which was regenerated regularly using sodium hydroxide. And on the right-hand side, you see the concentrations of the different PFAS that could be found in the groundwater of our test site. So we have some short-chain PFAS like PFBEA in a low concentration of 30 nanograms per liter, and we have higher concentrations of PFOA and also of PFPEA and PFHXA. The test site I'm going to talk about is the city of Rastatt. This is a city in the southern part of Germany with 50,000 inhabitants, and the drinking water of Rastatt is provided by 2 waterworks. Some years ago, they had 3 waterworks, but they had to close one because of a huge PFAS groundwater contamination. And one of the still working waterworks is the waterworks Rauental. They have a water throughput of 250 cubic meters per hour and an annual drinking water amount of 1.7 million cubic meters. Because of this PFAS contamination they have in the groundwater, they installed 4 activated carbon filters, each with 18 cubic meters, and they have to change each filter after about 17,000 bed volumes, which is an operating time of 6 to 9 months. In this waterwork in Rauental, we installed a pilot plant, which is shown on this picture. So we installed activated carbon filters, which are the big black filter columns, and we installed ion exchange columns, which are the smaller columns on this picture. And I'm going to tell you now something about the treatment performance of our combined process. So we start here, the PFAS concentrations in the raw water. I just want to show you that these concentrations are quite constant over our time. We investigated the raw water quality and we did our pilot plant experiments. And at the second point, after the activated carbon filter, we analyzed the PFAS, which you could see here on this slide. So a little bit like the pictures Alexander showed before, you could see the different breakthrough of the different PFAS, and the short chain PFAS, they break through earlier. So the PFBA starts after breakthrough of 5,000 bed volumes, and afterwards the substance PFPEA breakthrough after a throughput of about 10,000 bed volumes. And yeah, with longer throughput, the other long chain PFAS also can't be removed by the activated carbon anymore, and they break through the activated carbon filter on and on. And finally, you could see here the PFAS concentration after the ion exchanger. The dotted black lines you could see here were the times when the ion exchanger was regenerated, and in between these lines you see the concentrations of PFBA and PFPEA, and the concentrations of PFPEA, they were all the time lower than the detection level, and the concentrations of PFBA, you could see that there also is a kind of breakthrough at this single ion exchanger filtration times. So after a breakthrough, after a throughput of about 2,000 bed volumes, PFBA starts to break through the ion exchanger and the concentration increases. And if the ion exchanger is regenerated and is operated afterwards, the concentrations of PFBA, they decrease to zero again. And with an increasing throughput, they increase again. So we regenerated after different operation times, and we varied between 1 week and 2 weeks of operation times. And what you could see here, if we regenerate after 1 week, we could remove nearly all of the PFBA. If we made a regeneration after 2 weeks, we see a breakthrough of PFBA. So you could vary your efficiency of the process depending on the time when you start your regeneration of the ion exchanger. And here I show you something about the removal of an ultra short chain PFAS of TFA, which is the shortest PFAS which exists. And this graph is quite difficult to understand, but if you have a look at the pink lines, which is the effluent of the ion exchanger, and you also see the times when the ion exchanger was regenerated, you could see that shortly after the regeneration, the concentration of PFAS could be a little bit decreased. So with this regeneration, you could also remove TFA from your ion exchanger, but shortly after you operate your exchanger after the regeneration, your effluent concentration is at the same level at the raw water concentration. So if you would like to use some substance like this ultra short chain PFAS, this method can't be used because TFA is so badly absorbable. So yeah, this method can't be used for such substances, but it works for this short chain PFAS like PFBA and PFPEA. So I now come already to my conclusion. So if we would like to evaluate this kind of treatment, it is a question of when do we regenerate the ion exchanger. For example, if we do regeneration after 1 week, we have a yield of our process of about 99%, which will mean that we insert 100 liter of water into the ion exchanger. And after this ion exchanger treatment and ion exchanger regeneration, we will have 99 liter of drinking water and only 1 liter of PFAS containing regenerant. And for a further treatment, we only have to treat this 1 liter to destroy the PFAS finally. If you compare this yield with an operation of a reverse osmosis membrane, there we have yields of 80%, which will mean that if we treat 100 liter of raw water, we will have 80 liters of drinking water and 20 liter of a concentrate containing all PFAS. So you see that we could reach much higher yields if we use this ion exchanger treatment, including a regeneration. And what we have to do now is to make an evaluation of the treatment costs, where we check what are the materials costs for activated carbon and for ion exchangers and also for the chemicals. But this is ongoing work. And this was the end of my presentation. And now I'm going to hand over to Nassos Stasinakis for his presentation.
Thank you, Marcel. Okay, I think that now you can see my screen and you can hear me. Sorry.
Yes, we do.
Just a moment, please. Okay, so I'm Nassos Stasinakis. I'm professor at the University of the Aegean in Lesbos Island, Greece, and I'm going to talk about PFAS in sewage sludge. we participate in the ZeroPM project, and specifically to work package 7. In this work package, from our side, we have to study the fate of PFAS and some other PMP substances during biological and thermal sewage treatment, sludge treatment, and we have also to develop and improve some technical solution for removing PMP substances during sludge treatment. In the current presentation, I'm going to discuss a few literature findings for the current sludge production and for the existing knowledge and the research gaps on PFAS occurrence in sewage sludge and their fate during anaerobic digestion, and also for the risk for human health. And at the last part of the presentation, I will show some of our results. The ZeroPM project lasts for 60 months. At the moment, we are at month 30, so we have finished our laboratory experiments on PFAS, fate during anaerobic digestion and during hydrothermal carbonization, and we have started working on the pilot system that I'm going to show later. So let's start from the basics. At the moment, almost 80% of the EU population is connected to sewage treatment plants. This is an obligation of the European directive. So in most of the cases, we have secondary biological treatment, which is activated sludge process. From this process, we have the production of secondary sludge, secondary sludge, and the primary sludge that is produced also in sewage treatment plants that use also primary sedimentation. All these sludges, after different processes, they have to be disposed to the environment, or they have to incinerate it. The total amount of sewage sludge that is produced in the EU is quite high, is more than 8,300 kilotons per year as dry solids, and this sludge contains important concentrations of nitrogen and phosphorus. This means that can be used as fertilizer in the soil, but on the other hand, it can also be contaminated with some toxic compounds such as heavy metals or some organic micropollutants or microplastics. The reason for this is that during the wastewater treatment, a mechanism for the removal of these contaminants is their absorption to the suspended solids. So, for example, some organic micropollutants, according to their chemical properties, they are absorbed to the suspended solids, and afterwards, the suspended solids, due to gravity, and to the sewage sludge at the bottom of the secondary clarifier or primary clarifier. So, some results for the sewage sludge management in EU. According to the Eurostat data, almost 50% of the produced sludge is disposed to the soil directly in agriculture or after composting. And more or less similar picture we have in US. You can see in the right pie of the slide that 43% of the produced sludge in US is disposed to the soil. And in these amounts, we have also to add the amounts of sludge that in specific countries are disposed to landfills. In EU 27, you can see that 10% of the total produced amount of sludge is disposed to the landfills. In US, this percentage is much higher, and it is 42%. So if we take into account the sludge that is reused in agriculture and the sludge that is disposed to the land via the landfills, we can say that there is an increased risk due to the occurrence of micropollutants in the sludge and to the potential transfer of these compounds to the soil. Now, regarding PFAS, if you try to see the literature and find a relevant paper, we are going to see that the first paper that was public that was published and reported the existence of PFAS in sewage sludge was published in 2005, before almost 20 years, and it was published by some authors from Stanford University, from Oregon University in the US. In the next years, there were some publications. In 2015, me and the PhD student at that period, Olga Ravaniti, wrote a review paper. We tried to collect all the available information, and we wrote a review paper in order to present the concentration of PFAS in wastewater and sewage sludge. And according to this review paper that was published in Stoughton, 19 PFAS had been detected in sludge that period. And these 19 compounds were some perfluorinated carboxylic acids with 4 carbon to 18 carbon atoms. There were also some results for perfluorinated sulfonic acids and for 3 perfalkene sulfonamides. The concentrations of these compounds range between few nanogram per gram to some hundreds nanogram per gram. Now, which is its situation 10 years later? We're trying this period we're preparing a new review paper on the field, and there are more or less 50 research papers published on the field. We can see that the number of PFAS that have been detected is much higher, 178. In some of these studies, additionally to the well-known, let's say PFAS, in these studies there are also results for ultra-short PFAS, for new generation PFAS, such as Xenix, and for some PFAS precursors. So it seems that there is a need to include these substances as well in the future monitoring studies. Most of these research papers originate from Europe, US, and some countries in Asia, but there are specific countries or specific areas, Africa, for example, where there is a lack of data on the occurrence of these compounds in sewage sludge. Now, regarding the fate of PFAS during sludge anaerobic digestion, more or less it is known that anaerobic digestion is a common process that is applied worldwide in order to stabilize the sewage sludge and to produce biogas. So somebody would expect that many published papers could be found in the literature containing data on the fate of PFAS during anaerobic digestion. But this is not true. Most of the results, there are few results actually, and most of them come from lab experiments, and there is only one study that was published in 2021 from some researchers in Canada. They have monitored some 5 full-scale anaerobic digesters, and they took sums from the inlet and the outlet, and they calculated the sum for the sum of PFAS, their removal, and also the removal of specific compounds. And for 3 out of the 5 anaerobic digested, they showed a moderate decrease of PFAS that ranged up to 38%. On the other hand, there was no clear trend on the removal of specific PFAS, and for some of these compounds, actually there was an increase in their concentration of the outlet up to 95%. So it's not clear. We can say as a conclusion if the anaerobic digestion is able to remove specific PFAS. And some of the common problems that face these monitoring studies is the fact that they monitor a quite small number of PFAS, 5 to 10 more or less. Additionally, we have the presence of PFAS precursors that complicate to some extent the use of mass balances. And also, typically, the researchers collect grab samples. This is somehow problematic because grab samples are not so representative comparing to composite samples. Now, regarding the occurrence of PFAS in sludge-emitted soils, a similar picture, very few studies concerning the agricultural land contamination with PFAS. Most of these studies have been conducted under lab conditions, and there is only one study where an area was monitored where long-term application of biosolids had been conducted. So in this paper that was published in Water Research in 2022, the author mentioned that the concentration of the sum of monitored PFAS ranged up to 196 nanogram per gram, and he monitored a soil where the biosolids had been applied for 15 years. According to these results, PFOS and PFOA were the predominant compounds, while the PFAS levels were correlated to sludge loadings. Now, for the possible threats from the disposal of sewage sludge to PFAS, we have some results saying that PFAS, as they are mobile, they can contaminate the groundwater, or they can found in plants, animals, eggs. But in general, again, we have limited knowledge on the uptake of PFAS from sludge-emitted soils to plants, and on their leaching to groundwater. There is lack of long-term experiments. On the other hand, there is a recent article that was again published in 2022, where, according to the authors, dust from the areas where biosolids have been applied could also be a carrier, let's say, for transferring PFAS and affecting the human health and the quality of the environment. Now, let's pass to some results from our experiments. In our lab experiments that we conducted during the previous 2 years, we studied two different technologies. The first technology was modified anaerobic digestion. For this reason, we conducted in the lab batch experiments and continuous flow experiments, and we studied the fate of 7 PFAS during anaerobic digestion. And so we had some experiments and some flasks where conventional anaerobic digestion was applied, but in parallel, we also modified the process, added some conductive materials such as GAC or applying voltage. We also tried to study the role of sludge pretreatment. For this reason, we conduct experiments with thermally pretreated sludge and ultrasound pretreated sludge, and we also check the role of temperature during anaerobic digestion. For this reason, we run experiments under mesophilic and thermophilic conditions, and we could say that according to our results, we didn't see any removal of target PFAS during conventional anaerobic digestion, and there was no important differences under mesophilic and thermophilic conditions. On the other hand, we showed that in the reactors and in the experiments that we had added GAC as conductive material, we show an increased removal of PFAS. For some of these compounds, the removal was up to 60 or 70%, as you can see in this figure. I have to mention here that in our experiments, we analyzed these compounds both in the dissolved and the particulate phase, and we applied mass balances to calculate the removal. So we are quite sure that this removal is not only to sorption, but is possibly due to biotransformation of these compounds. In parallel, during these experiments, we collect samples and we monitor the performance of the whole system for the biogas production, for the methane production, for the production of volatile fatty acids, and we also characterize the biomass in the bioreactors. And an interesting observation was that we saw in the reactors containing GAC an increased concentration of specific bacteria, which is called Acinetobacter, and these bacteria, according to the literature and previous papers, it seems to be involved in the biotransformation of PFAS. The second technology that we work on this during ZeroPM is hydrothermal carbonization. In these lab experiments, we applied different pressures, different temperatures, and different pH values to see if there is any removal of PFAS. According to our results, we saw a quite high removal of PFAS, higher than 85% under all tested conditions, with exception of PFOS and PFUDA. We also showed that with the increase of temperature, we can achieve a higher PFAS removal. And taking samples also from the gas phase, we also detect some trace amounts of specific PFAS in the gas phase. Again, we detected these compounds in the dissolved and in the particulate phase, and we applied mass balances. And you can see from the figure for some of these PFAS, the removal is almost 99%. It's very high. Now, the next work for the next 2 years, we have to operate the pilot system. It was constructed and started the operation in March 2024. We have the obligation to operate and monitor the system for 2 years. So we are going to collect samples from the different steps. As a first step, we have pretreatment of sludge, and we have two different options for sludge pretreatment, thermal and ultrasound. Afterwards, we have the anaerobic digester. Afterwards, we have the hydrothermal carbonization. And as a last step, we have a solar drying. So we are going to monitor the system and the contribution of different steps for the removal of PFAS, also for the removal of some other PMT substances. And we are going also to evaluate the performance of the system for the economical cost, for the energy consumption, and for the biogas production at the anaerobic step. To finish and summarize, based on the literature results and also to our research findings, we could say that several PFAS are found in sewage sludge and concentrations up to some hundreds nanogram per gram. Their fate during anaerobic digestion is not clear. However, biotransformation seems to be possible for some of these compounds and for some operational conditions. Regarding the hydrothermal carbonization, seems to be a promising technology for removing these compounds. There are some needs, many needs actually, for future research. So there is a need for the presence, more data on the presence of ultra-short PFAS, new generation PFAS, and PFAS precursors in sewage sludge in monitoring studies. There is a need for more data on the role of specific microorganisms on their biotransformation and on the biotransformation pathways of these compounds. More data are also needed on the fate of PFAS in sludge amended solid and on their effects to the environment. And in general, I would like to say that most of the results that are available at the moment in the literature are lab experiments, and there is need for more results from long-term experiments and also from the operation of pilot scale and full-scale systems. Thank you very much.
So we can't hear you, Helena.
Okay, can you hear me now?
I can hear you now, lovely. And also, if you just pop your presentation into presentation mode.
Definitely. Okay. There we go.
Lovely.
Thank you. Hello, everyone. My name is Helena, and I'm a proud presenter of Work Package 7 in the Scenarios project. Scenarios is a EU-funded project within the Zero Pollution Ambition, and we have 19 partners in our team from 11 countries. We do investigate 3 main areas. It's PFAS determination by sensor-based techniques
systematic hazards and risks assessment of next generation PFAS, and PFAS remediation by removal and destruction. And that's what I am here to present today. So these are my partners for the work package 7. I'm presenting to you a specific technology and its innovative treatment method for providing a sustainable option for PFAS water treatment. We have today listened to some fairly standard and traditional methods for removal of PFAS, and that's including filter media such as activated carbon and AIX. They are great at absorbing PFAS when they get to work in their optimal environments, but unfortunately not we all have is optimal environments. So they can for sure deliver 99.9 removal efficiency for all PFAS, as they say, but for how long or short? Well, that's different to the specific waters you have, because it's about media and contact. And if you have other substances in the way that can't get contact with the PFAS, you will get less capability of your filter media. So water chemistry is important. Co-contaminants, suspended solvents, organic materials, salts, everything interfere with filter medias. And today we have seen some fairly easy waters that have been having troubles due to something like DOC. There are pre-treatment systems that can amend this, that can help you to treat other competing contaminants and so on before treatment. But then you also have the production of sludge and all the service that needs to be taken care of. There's another, other solutions are nanofiltration or reverse osmosis. They're really good at removing all PFAS, but they also create a brine. So there's always a problem with the waste production and how much that will be, service, pre-systems, and the whole PFAS equation. So I'm here to talk to you about SAF. It's a surface active foam fractionation model. It was the first foam fractionation unit on the world market to me known. We took it to market in 2021. It works by just removing PFAS by adding bubbles to water. So, and how does this work? Well, perfluorinated substances, as PFAS has a hydraulic head that loves the water and a hydrophobic tail that hates the water. So when we introduce the bubble to this water, the tail can stick to the bubble and it can have its perfect environment. The head gets to swim and the tail sticks to the bubble. And we can remove the PFAS as a foam. And for long chains, this works really well for any water, almost no matter what else is in the water. However, for short chain PFAS, it is less effective and we get less removal rates due to that. So this is why we are trialing this, the SAF method, because it's a very robust treatment option and has no filter medias. It is not sensitive to PFAS levels, high or low. It removes PFAS if it's in there. It's not so sensitive to suspended particles, dissolved organic matter, dissolved organic carbon, salinity, pH, and so on, or other co-contaminants. We are not using any pre-treatment steps that needs to create any sludge. We are using bag filters to protect the pumps, but that's about it. We have shown that the foam fractionation is capable of removing PFAS 4 and PFAS 6 up to 99.9%, non-detect usually, using no consumables or additives while producing very little amounts of waste. The electricity used is only 0.7 kilowatt hours per cubic meter treated, so it makes it very sustainable in that way too. Waste production, where an example that we've seen is for a leachate, which usually produces a lot of waste, we have less than 5 cubic meters per 100,000 cubic meters treated. And that's because of the concentration steps that this SAF method is using. Some typical removal rates that is seen for surface active foam fractionation, where we only use the bubbles. You can see here, as I said, for the long chains, we have excellent removal rates. PFAS 4 and PFAS 6 is usually down to non-detect or from 99% and upwards. And then you can see how the removal efficiency drops for the shorter chain PFAS. You can see for firefighting water, it's treated for a pilot refinery. You can see that we are removing nothing at PFBA, but then again, for some waters, we do have some short chain removal, so it varies a little bit. This is just a guide to see what we can do for different waters. So SAF is produced by Epoch Enviro in Australia, and NVTech is exclusive distributor for Europe and UK. So the removal process, how does it work? It's 3 steps where we bubble bubbles in water. We use the primary, the secondary, and the tertiary step. The primary step, that is just bubbling bubbles in water, and that can be found with normal foam fractionation units. It's 10 times the initial concentration step that we do. So we remove all the PFAS and 10% of the water, and then we release the water. The second step is approximately another 1,500 initial concentration. We are now only minimizing waste. The treatment step is only the first step. We then do it once again. We bubble through water in the tertiary step, and we have up to 2 million times the initial concentration and very small waste volumes. It's easy to talk about it, but it's much easier to understand when you look at it. So I will show you a video just in the next slides. How it works is that water is coming in to the first tank that we have. And then when this is full, it kicks off the first primary where we bubble through water. Foam comes up, as you can see here in this photo, and we remove the foam. The water comes in, the next one is filled, so it's like a sequential batch system. So the inflow is constant, the outflow is constant, but we work in batches. When the treated water is released and the foam is collected in storage tanks at the back. When this is full, these 2 units here, the secondaries, turn on and we do a second step. And then we remove the foam and the water is released back to the front. So we do it once again. We do not release the treated water from the second step. When this tank is full of the secondary foam, we do it once again in this tertiary step unit, dragging out the last piece of water, making it to almost minimum amounts of waste. You can see here to the left, this is a leachate where we have no pre-treatment, but we just treat the leachate coming in, and you can see how we remove the PFAS as a foam. It's a pretty thick foam, high foaming capacities of these waters due to organics and all other things that are in there. It's a totally different story for a groundwater, which you can see here in this photo, where you have very little amounts of foam production and a much clearer, different water. The secondary step is much different. We have a much higher concentration, and we now remove the PFAS from the water just to minimize the waste. We do that then in the third step, as you can see in this photo, and now the concentrations are really high, and we have minimized the amount of water in there. It is a container unit that's come to site. It's plug and play, one say, but if you do that, you don't work with water treatment because nothing is plug and play with water. But here you can plug it in here and you have the released water here, and then you're ready to go. It takes about 1 to 2 days to get it up and running and fine tuning. Every valve, every pump, everything that moves in this container is controlled by a sensor. Sensor feeds into the HMI. And we have all data such as energy use, waste production, how many cycles, amounts treated, and so on. We also get alarms if anything happens. We are able to watch it remotely by cameras as well. This you can see here. This is a video of me looking at a site, one of our sites, so I can see that it's working. We work with local staff at the projects that we're on. So with our team in Denmark, we can help them out to run the place where I'm about to present to you. So in the Scenarios project, we are trialing this pilot plant at 2 sites, and the first one is already started. We're very happy to be present at the Korsør Rescue Firefighting Center training ground, where it was the ground zero for PFAS in Denmark. So we are treating surface water runoff and groundwater from the site. And here the history is that the water was initially running off a hill and cows were drinking it, intoxicating the cows and also intoxicating the whole society that was living off the cows. So a very tragic story. They have now turned this place into a test center for PFAS. This is what the Danish government have done, and we are proud to be the first to trial new technologies at these sites. And I can see now that we also have the video, so you can actually see what the sites looks like. Just going to take you through that. We started the treatment, the Scenarios project of the groundwater using staff in November 2023. So we have now been going on for a couple of months, and those are the results that I will be presenting now. What you saw there are the primary units, and here are the secondary units. So this is what it looks like on the inside. It's always good to see a good film. Here you can see the PFAS removal that we are doing on site. It is heavily contaminated groundwater, so we do have a lot of foaming. All right. But we didn't start with a pilot scale in the field. We started with a bench scale, which we are doing in this mini system that we have. It is situated at the Envitec laboratory in Stockholm, and where clients can send waters from all over Europe to trial their waters. We have done this with the conserved water, and here we are using untreated water just to see what removal rates we would achieve using only SAF. The waters weren't very foamy, so we had to tune it a bit to get it working. So even though it has quite high PFAS levels. So we did the treatment, we removed the foam, we took the sample from the unit and sent it to Eurofins for analyze. And here you can see the results from the first trial. We have 110,000 nanograms coming in and 73,000 going out. You can see that we are, as planned or as we thought, are removing the long change down to below the detection levels. And then for the short chain PFAS, the levels drop. In these waters, we have quite high concentrations of short chain waters. There. So this was the first step we did. It was the lab scale. And after that, we have, as you saw on the film, we have done the full scale. And these are the results from that. So here we have 3 different trials, 3 different sampling events, where we have trialed 3 different settings. So treatment times, hertz on the pumps, and so on, that we get to play with to see if we can create more foam or make more PFAS come out of the water. These waters were, the water coming in now is a bit lower than the 110,000 in the lab scale. You can see we have about between 30 to 60,000 nanograms per liter coming in. And you can see for all 3 settings, we have a PFAS-4 removal of about 99%. And then we have dropping removal rates for short chains, just that we have seen in other projects and we did in the lab scale. So for the sum of PFAS, we are working around 70% removal down to 50, somewhere like that. So we know that it's working for long chains, but how can we make it work for short chains? So it is by attracting surface active PFAS compounds to an air bubble. And as the short chain PFAS are not a surface active, we don't have the same ability to move them. We do see that in different waters with higher complexity, more foamy waters, we do get a higher efficiency. And that's where the idea came to see if we can increase PFAS removal rates by adding special additives and surfactants. We at Envitec have been working with Alonia before, Alonia in the US, it's a US research company. And we are also in the scenarios project researching several additives to trial within the project. So these are just the first trial that we will see here today. This is the lab scale trial that we have done, and we are using a booster substance done from Alonia in the US. And if you remember the really low foamy water before, now it's a totally different story. We have added very low concentrations of a booster. The booster substance is toxic to aquatic environment in high concentrations. But however, we have just received results. I couldn't show them today. They were so new that we removed completely all additives that are made in the process, in the foam, and there is nothing left in the waters after treatment. So we were very excited to see this, that we got this big foam production and that we are removing the additive in the process. But what about the results? So here are 3 different results. So we have the incoming water, we have the outgoing water using no additive, and we have 3 different doses with the additive. And what you can see here is that we are increasing the removal rates for the PFAS-4 for the long chains even further, but we are also reaching higher removal rates for the shorter chain PFAS. You can see, for example, for PFAS, we have remarkably high removal rates. We are down to 2.4 nanograms from starting position of 4,500. We're removing PFHXA, which is another problem for us, down to really low numbers. We are also looking at PFPEA, which is also really troublesome to get. The only one that we don't really touch it is the PFBA, which we are having problems with, which we knew would be a problem. In this water, we do see, however, that we have an increasing amount of PFAS. We have not seen that before, and we will have to do new trials to see if there's any cross-contaminants or what that depending on. 3.9 is less than 10, so that's fine, but this is a little bit increasing. But other than that, we are getting really good removal rates, and we are super excited about these results. Yes, I should show you this slide as well. This is just looking at the percentage differences and not just the concentrations. So you can see here that for PFBS, we are up from 9% up to almost 99, 100. PFBS also really big increase, as you saw in the slide before. And the next step, super excited, is to do the first full-scale project in the world using additive boosters with the SAF units. It is fitted for this project with a dosing system. So we are just about ready to go into the field and add this. So I would like to keep you to stay on the scenarios homepage to see updates about this, because we are very excited. The second project that we are to do is the landfill leachate that we've been talking about. That's a troublesome water with high organic loading, DOCs and TOC problems that we heard of today. And from what we have seen in the full-scale projects that has been done before, we are getting really good removal rates for long chain, but none for short chains. And with the complexity of these waters, we didn't know what to expect if we could actually reach it using additives. So this project you see here is the water that we're pumping straight into SAF in Sweden. We are treating it. We have treated about 300,000 cubic meters. We are producing only 5 cubics a year of PFAS concentrate, and we are using very low volumes of electricity. So we have done the first lab scale trial for the scenarios on leachates. And just to show you, this is without additives. So as a leachate is, it has a very good foam. No surprise there. The problem with leachate is more to handle the foam actually than to get foam. And that's where the concentration system is really working for us. So this is a no additive trial. We have also done it with additive, and I will show you one of the trials that we have done with the same water. So it might not to an untrained eye look much different, but what we see is that the foam is much more stable. We have a little bit of an increase, but you can see that the density is really much higher with this additive. This is once again an aquatic, a toxic to aquatic environment in high concentrations. We're adding very, very little dosing, and we are removing it totally from the outgoing treated water. So the results from this bench scale trial, you can see that we are removing the long chains with no additive, which is expected. For this water, it works really well. We have a really good removal rate for many PFAS, but we do see for PFHXA, PFPEA, PFB, and PFBS, which are the usual suspects that we have a hard time to catch. We do see that we have a really good reduction rate for PFHXA, a little bit, and at least for PFPEA, well, a little bit. When we up the dose a little bit, we have about 1/3 of the incoming concentration. We don't touch PFBA, but we do, however, remove down to below the detection limit for PFBS, which is really remarkable, we see. And we see that as a really positive thing for going forward. Here are the removal rates, just to show you that. You can see here where we have the PFBA, we are not doing so well, but on the PFBA, PFHA, and PFBS, we are doing really well. When we do this in full scale, we will use two-step concentrations to see how much waste we will be producing. And so just some data on the treatment process. We can do a maximum of 30 cubic meters an hour, but the minimum is about 7 for this unit that we have on the pilot site. We use still the 0.7 cubic treated. We have verified that. And we also follow the waste production that has been given from EPOC, so the very low waste for groundwaters. We have now shown that we can remove short chains using additives, at least in a larger proportion. And we are also looking into taking this waste that we are producing and destroying it by several methods that are on the market today and offered as a solution. And maybe then to also produce a closed loop project within the scenarios project. So it's very exciting for us. And yeah. I hope you follow us to hear the rest. Thank you.
Okay, thank you everyone for all of the great presentations and discussions of the different techniques and technologies that we're using in our projects. We have time for a little bit of Q&A. So if anybody else has a question, please just pop it in the chat and then I'm going to read it out. We've had one question that's come in, which is for Nazos. So Nazos, the question is, will you be looking at pyrolysis as a technology to eliminate PFAS in sludge?
Thank you, Sarah. No, in the ZeroPM project, we do not intend to examine the role of pyrolysis. I know that there are already some interesting published results, and there is another research project which is called Sludge Effect, and our coordinator in ZeroPM, Hans-Peter Arp, coordinates this project, and I have seen the results, and they are very encouraging on the removal of PFAS during pyrolysis. But in ZeroPM, when we are writing the proposal, we decided to focus to hydrothermal carbonization because in this process we do not have the obligation, let's say, to dewater the sludge before the process. So we can direct transfer the sludge from the anaerobic digester to the hydrothermal carbonization reactor. So we are quite curious to see if this process can also remove these compounds, and also which will be the characteristics of the final products, the hydrochar liquid and for sure the hydrochar. Also, we would like to see if the hydrochar could be used in as a soil amendment, its properties, and all these things.
Okay, great, thank you, Nazos. And we have another question for you actually, so just stay there. The question is, have you measured PFAS concentrations in the hydrochar generated during the hydrothermal treatment of the sludge?
Yes, we have. As I mentioned before, in our experiments, we analyze both the dissolved phase and the particulate phase at the start and at the end of the experiments. So we know which is the distribution of these compounds between the two different phases. And when calculated the removal, we have applied mass balances using the concentrations in the dissolved and particulate phase. And based on all this analysis and calculation, I said before that the removal was very high, up to 100% for some of the target PFAS.
Great, thank you. Then we have a question for Alexander. The question is, what would be the price carbon dioxide footprint for the production of the resins and the activated carbon? And how would the maintenance look? So for example, can the resins be regenerated? Obviously that affects cost, doesn't it? And then a second part is, why is DOC not removed before the GAC and the resins in the treatment train?
Thank you for the question. Yes, first, what would be the price? This is, we haven't looked very much into it. I think, but I know that my colleague Marcel from ZeroPM has done more on this. I think what I know from his studies and from literature is that the price of the ion exchange resins are in the range of 5 to 10 times higher than the price of GAC. The ion exchange resins we study now are not regenerable, so this would be an issue. You have to calculate the capacities versus the price. The higher capacities versus the much higher price also. So there's yeah, you have to see whether this works out. And maintenance, as I said, we didn't study the regeneration. If you would regenerate the ion exchange resins, which is an option, which is also studied at German Drinking Water Center, which Marcel presented, you would have to take care of the regenerate, of course, and treat it or dispose it of. Yeah, why is the DOC not removed before the GAC resins? Yeah, this is actually the great question here, because it's not so easy to remove. The idea was to do this in this kind of setup, but you would have to find an adsorption process to remove specifically the DOC, which is not possible. We see that the DOC is also breaking through quite early, but the idea would be to get rid of the DOC beforehand and then have higher capacity, but also do it in an economic way. So this is what we're trying to do, and to find a selection of carbon and ion exchange, maybe a combination of both, or find another way to remove DOC.
Yes, you have the next question as well.
Yeah, if it's okay, I go ahead for the next one. What are the disposal options in Germany for the modified clay adsorbents? I don't know, actually. That's actually a good point. We would have to check whether you can dispose them off, or I guess you cannot regenerate them. So that's a good question. We have to study more. Yeah.
Okay, thank you, Alexander. So then we have a question for Helena. And the question that you have, Helena, is what are the current best available options for concrete treatment to achieve a closed loop process? And we can't hear you because I don't know why, but...
No, it was me. I was muted. Sorry. I was just wondering, could you repeat that for concrete?
It says, what's the current best available option for concrete treatment to achieve a closed loop process? So I guess...
Concentrate treatment. Concentrate.
Sorry, concentrate treatment.
Sorry, I should have got that. Okay. Yeah. So what we do see now in Europe is that the prices for incineration are fairly low, and so it is hard for other destruction technologies to measure that. We have successfully trialed electrochemical oxidation, UV activated defluorination as well. And of course, supercritical water oxidation is also proven for the concentrates. And there's a fourth one that we trialed that I will remember. They all work. It's just a question of money, how much it costs. The electricity used for none of these are excessive, I would say. It's more the cost of the whole process. Of course, there's a lot of research and science and building these things that should go into it. But we are getting closer to having options that are meeting the prices for the European market. And that's what we're working for now, to have options that can meet that. So they all can destroy the PFAS. We've shown it's just really a matter of cost.
Yeah, this is the thing, isn't it, with a lot of the different treatments, actually. Thank you, Helena. So we have a question for Ali B. And the question is, are you planning to evaluate the impact of adding a PFAS adsorbent on soil quality. Thinking in terms of removing PFAS from agricultural soils, maybe it would be also then interesting to look at the potential adverse effects on soil function. So, I mean, there's a lot of research about these kinds of topics with different pollutants. I myself haven't seen too much related to PFAS, but Ali, are you there to answer the question? And if Ali is not there, we could always get it answered afterwards.
Excuse me, it's for me, Ali Batik or Ali Aidar?
We don't see you, but that's okay. We sort of hear you. There we go.
So could you repeat the question, please?
So the question is, are you looking at the impact of adding PFAS adsorbents on soil quality? You know, if you're thinking of removing PFAS from agricultural soils, would there be any potential adverse effects on, for example, soil function? Is that something that you're looking at in your research?
In fact, in our research, we are going to inject a fluid to remove PFAS from soil. We're not going to add anything. Soil and groundwater. In fact, the idea was to use the mixture of this non-Newtonian fluid to remove it from groundwater and soil. There's no additive as a PFAS sorbent or some other things.
That's okay. Great. Good answer. Like I say, there is a lot of research where people have looked at using adsorbents in soil for different pollutants.
Yeah, in fact, in our work, we'll go use this non-Newtonian fluid to extract PFAS from soil and water. We are not going to adsorb it. In fact, we are not going to desorb it. It's another, the other method, let's call it.
Great. I don't think that we have any more questions. If anybody wants to pose a question afterwards, then they can just contact me. I think it's the easiest, and I can send it further to one of the speakers. And with that, I would like to thank everybody who's listened today for taking the time to hear about the work that we're doing in our 3 really exciting research projects. And yeah, have a good rest of your day. So thank you, everyone.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.